Okay, so problem P2B.5 says, a sample of 2 moles of CO2 occupies a fixed volume of 15.0 decimeters cubed at 300 Kelvin. When it is supplied with 2.35 kilojoules of energy as heat, its temperature increases to 341 Kelvin. Calculate W, delta U, and delta H. And we are told that we can assume that CO2 can be described by van der Waals equations, which I have written here as P equals nRT over V minus NB minus A times N squared over V squared. I have also given you guys, we're also given the A and B terms, so this is this and this here, for our van der Waals equation, which for our A, it is 3.610 atm decimeters to the 6 moles to the negative 2. Our B is going to be 4.29 times 10 to the negative 2 decimeters cubed moles inverse. So with all of this, we are being asked to calculate our work, our delta U, and our delta H. So first thing we do, I think in my opinion the easiest thing to do would be to calculate our W. Now, W, so work is defined as negative P external, so our negative external pressure times our change in volume. Now, we were given something pretty major that will give us a more easier time doing the work, unintended, and that is that this is at a fixed volume. And this is very key, this is very important. Why? Because at a fixed volume, V is equal to VI, which is equal to VF. So volume is constant. Volume is our constant. And if you know basic calculus, the derivative of a constant is just 0. Our volume is constant, therefore taking the derivative of our volume, our infinitesimal changes, is going to be 0. Why is that important? Well, this is delta V, right? We're at a constant volume. Derivative of constant is 0. Our volume is not going to be changing. This volume term is not going to be changing. So this term will go to 0, and therefore work is going to be equal to 0. There's 0 work. Yay! And then this will make the other part of our life more simpler, because then we're being asked to find delta U. Now, for delta U, so our change in internal energy is delta U is equal to Q plus W. So our delta U is the sum of our energy as heat and our work. But we just found out that our work is equal to 0. So this too goes to 0. So therefore, at a fixed volume, at a constant volume, delta U is equal to Q. And well, guess what? We were told that it is supplied with 2.35 kilojoules of energy as heat. Funny enough, we were pretty much given the answer in our problem. You just had to know some thermodynamics. So we were already kind of given the answer in our problem. So delta U at constant volume, delta U is equal to Q, which is equal to our 2.35 kilojoules. So far, so good. However, now we're going to get to some of the more grunt work of our math. So we already found out our delta U. Now we're trying to find our delta H. So delta H is equal to delta U plus delta PV. Now this delta term can be distributed to either our P term or our V term. We were told that we have a fixed volume and we're increasing our temperature from 300 Kelvin to 341 Kelvin, which means one thing, our pressure is what is changing. So we're going to distribute this delta term to instead our P. So this will be delta U plus delta P times our constant volume. Well, what is our change in P? We have to use van der Waals equation to find our P1, PI, P initial, and P final. So we're given our A terms and our B terms. Now we have to find our P initial and our P final. So with that, we are going to first I will first do our P initial. So that's more easier for me. So P initial at 300 degrees Kelvin. Some people choose to work in molar volumes. There is a van der Waals equation written in molar volumes, but I personally choose to have it written like this, where I have my N and my V terms like explicit. So our initial volume, so PI, to be kind of long, PI is going to be equal to our number of moles, so that is 2 moles, times my R value. I'm personally going to work in decimeters cubed, and I'm going to get ATM as preferably. I want to use ATM to be my ending pressure. So I'll do 2.0 moles times 8.20574 times 10 to the negative second power, decimeters cubed, ATM, Kelvin, molar inverse, times our 300 degrees Kelvin, over our volume, which was 15.0 decimeters cubed, minus 2 moles, times our B term, which we have it as 4.29 times 10 to the negative 2 decimeters cubed mole inverse, minus, I hope this gets included, minus our A term, which is 3.610 ATM, decimeters 6, moles minus 2. I have to put it down here, times our number of moles, so we have our 2 moles, and our volume, decimeters, 15.0 decimeters cubed. All right, it's very long, but we're going to cancel a lot of terms. So let's do some canceling. First thing we have here is that we're going to be left with essentially mole squared, and we're going to have decimeters to the 6, right? This will cancel with this, and this will cancel with this. So we're going to be left with an ATM term here. Over here, our moles are going to cancel, our kelvins are going to cancel, our moles are going to cancel over here too, and we have decimeters cubed here, decimeter cubed here, decimeters cubed here. They're all going to get canceled. So we're going to be left with also another ATM term, and when we have that, when we do all of this math, we are going to get around your P initial to be around 3.237 ATM, or we want to get this into SI units preferably. I will convert 3.237 ATM to pascals. When you do your conversions correctly, you should then get, when you convert 3.237 ATM to pascals, you will get 327,989.025 pascals. The reason why I want to do pascals is because pascals has our units of kilograms, meters, and seconds. And so in the end, we're gonna get our SI units that we're gonna convert to our joules terms. And you'll see that towards the end. Also, the reason why I choose to work in ATM from the beginning instead of doing conversions is that our coefficients are in ATM. So this A coefficient is an ATM. So I prefer to work in ATM from the beginning because my A term is an ATM. So why not, instead of doing conversions in the beginning, I can just do it towards the end. I know how to do from ATM to pascals. You can look it up on Google. So it just makes it easier for me personally. I want to get rid of all my terms and just have ATM, and then I can do my conversions later. Because this is our A is an ATM, decimeters 6, moles -2, and I just want to do not too many conversions. So basically, so we have our P initial. Now, our P final. So P final, you just do the exact same thing. For P final, you just have to substitute your temperature in. Instead of 300, you would have to do then 341. Everything else should change. Your moles should stay the same. Your R should stay the same. Your volume, of course, should stay the same, except for your temperature. So when if you were to switch out 300 Kelvin for 341 Kelvin, same thing. Same thing, honestly. You just have to switch out one of these terms. To save you guys some time, when you do this, you will have then a final volume, a P final volume of 368.8 ATM. Whereas I convert it, I just convert it to then 373,686.6 pascals. Now, why do we do all this work? To find our delta P. Delta P is equal to our final pressure minus our initial pressure, final minus initial. When you do that, you then get basically, using the Pascal term, by the way, I then get 45,697.575 pascals. So, we're almost there. We are almost there. Now, let's go back to our enthalpy. We found our enthalpy. We already found our delta P. Now, let's find our enthalpy. So, there's a reason why I've been working in pascals, and you'll see why. So, our delta H is going to be equal to our delta U, which we said was 2.35 kilojoules, plus our delta P terms. Now, for pascals can be written as kilograms, meters minus 1, seconds minus 2. Joules can be written as kilograms, meters squared, seconds minus 2. And I think you know where I'm going with this. I'm going to break up our pascals into its core SI units. So I'll break up this pascals right here. I'll break this up into 45,697.575. Instead of be kilograms, meters minus 1, seconds minus 2, times our volume. When I convert decimeters cubed, this 15.0 decimeters cubed to meters cubed, it will basically just come out to 0.015 meters cubed because, you know, take the term, take the decimal, shift it 1, 2, 3 places to the left, and you have your decimeters cubed to meters cubed. So it's going to be 0.015 meters cubed. Now when I do all of this, my meters term, this term here will go to meters squared. Keep my kilogram. I now have my meters squared, my seconds minus 2, and would you look at that? This looks like our joules. So this will then be 2.35 kilojoules plus 685.46 kilograms meters squared, seconds minus 2. When you add these up, well, when I basically convert this into kilojoules, when I'm working in kilojoules, I will then get my delta H is going to be 3,035.46. I guess I could convert this actually to joules. I guess it would be much more easier for me to work in joules. Actually, never mind. If you were to work in joules and convert everything, including this, to joules, you will then have 3,035.46 joules. And so that's it. This is how you do problems P2B.5. Oh, your work should be 0. Your delta U should be equal to your Q, which should be equal to your 2.35 kilojoules. You then get your P initial and your P final, then you get your delta P. And then you plug this into your equations. You keep everything in its SI units to get joules. And when you do that, you should then get your enthalpy, your delta H being 3,035.46 joules. See, not so bad. Thank you so much. Have a great rest of your day.